is the last one, palladium catalyzed hydroxylations. And this is literally a displacement of X by OH using palladium catalyst. The mechanism obviously is different from what we've discussed so far. And just to give you examples, this is something that has been developed over the last decade or a little more, and got the Nobel Prize. Palladium catalyzed chemistry in general got the Nobel Prize in 2010. You use, for example, chlorobenzene or bromobenzene, iodobenzene. Substituents can be pushers, acceptors can be at any positions. The chloride or the halogen is displaced by hydroxide. All you do is treat it with hydroxide, KOH, sodium hydroxide. The palladium catalyst, it's in the presence of a ligand, trialkyl or triphenylphosphine, and typically people heat it a little bit. This one was done at 100 degrees, 90% of the phenol. The catalyst is not heterogeneous, it's a homogeneous catalyst. So it's an organometallic compound, defined structure that goes into solution. One example is palladium tetraphosphine, tetratriphenylphosphine. Okay? That's the same triphenylphosphine we used in the Wittig reaction. Okay? Phosphine is one down from nitrogen, it's got an electron pair, it's very polarizable, big electron pair, and it's a great ligand to palladium. In the transition metals, instead of the octet rule, we have the 18 electron rule because they're d orbitals, 5 d orbitals. You may or may not remember that from 3A, and that means you add another 10 to the 8 already there, so it's now the 18 electron rule. But otherwise, the same electron counting applies. So 18 electron is closed shell, and these ligands help donate electrons to get the metal to adopt what amounts to a noble gas configuration. But all you have to do is write palladium in a synthetic scheme. So here's another example, MEDA, and here's now an acceptor. Doesn't matter, quantitative, you get the phenol. This also works for other nucleophiles. We're just going to do it for amines because we're going to do amine synthesis last in this chapter, and this also works with palladium, so you can take pusher and MEDA now with an amine, 98% displacement. Ammonia itself works. You get displacement and high yield. So you can do this with hydroxide and with amines, substituted amines, alkoxides, and they all displace the halogen. Mechanistically, it's actually rather simple, but we're not going to go into the details because it's organometallic chemistry. But topologically, what happens is the palladium inserts into carbon X bond. With its d orbitals and stuff, it manages to maneuver inside, cleave the bond, and so you're generating a phenyl-palladium X species and leaving out all the phenyl substituents that are there to enable the 18 electron rule around palladium. But that's the essence. And then you can readily imagine this is like a metal salt. And metal salts exchange their anions, and so with hydroxide, X exchanges for hydroxide. And then it just de-inserts. These are slightly high energy intermediates, and this is then the thermodynamic sink. So things go from left to right because that's thermodynamically favorable. That's basically what happens. It's really incredibly simple. Beautiful reaction, and not surprisingly, got a Nobel Prize. You can use that in many, many applications. All you need to be able to do then is introduce the halogen into an arene by electrophilic halogenation. You already know how to do that. So it extends your halo aromatic chemistry also to phenols and benzenamines. So what sort of chemistry can we expect? It's alcohol chemistry. So there's very little new stuff. Alcohols are basic. They're lousy bases because oxygen is very electronegative. But you can protonate. Obviously, you can protonate alcohols. That's a step we've been writing forever to turn OH into water, good leaving group. pKa of methanol is minus 2.2. Not surprisingly, this pKa is much worse because the electron pair on phenol is involved in delocalization into the benzene ring. So it's not as available as the electron pair on methanol. So that drops the pKa. But you could still do reversible protonation. So as far as you're concerned, you can protonate phenol just like you protonate an alcohol. There's a big difference, however. This protonation, while it turns this into H2O, which is normally a good leaving group, that H2O won't leave. Because what it would leave behind is a phenylcation. And that's absolutely not good. Okay? With nitrogen, this barely goes, right? But not with water. Water doesn't leave. So there are no phenylcalines ever. On the other hand, you can hydrolyze phenyl ethers poorly because phenyl ethers, like normal ethers, are extremely stable species. You may remember chapter 9, we can hydrolyze ethers, but only when we use concentrated HBr or HCl. And what happens is you protonate, and then the counterion, chloride or bromide, does a nucleophilic displacement on the ether. In the case of a dialkyl ether, where this is an alkyl group, the attack of X can go either on the right side or on the left side. But for phenyl, it only goes attack on the right side because only the right side is an alkyl that's sp3 hybridized, and it can do SN2 reactions. We can't do SN2s on an sp2 carbon. We just went through this. Okay? So that selectively liberates the phenol and makes a haloalkane. So that's a slight twist of the hydrolysis of phenol ethers. How do we make phenol ethers? Williamson ether synthesis. Okay? And we just did actually in our synthetic example, we just did that. Okay? There's a Williamson ether synthesis. The protection step of this phenol with benzyl bromide was exactly this step. So a little bit of base makes the phenoxide. The phenoxide does an SN2. You get the corresponding ether. Nothing new. We can make esters, nothing new here. So a phenol with carboxylic acid will make an ester. Phenol with an acyl halide will make an ester. Phenol with an anhydride will make an ester. I'm just giving you the anhydride example with this particular guy because this is actually the industrial synthesis of the corresponding ester, and that ester is aspirin. Okay? Aspirin, in my opinion, the safest drug on this planet. Okay? It's consumed to the tune of 10,000 tons per year. Okay? So while some people complain about side effects, considering the scale at which this is consumed, I think the discomfort for some people who are sensitive, the stomach, it irritates the stomach walls for some people, particularly if you take a lot of aspirin, if you have arthritis, for example. The incidence of that happening is on the order of somebody complaining about drinking too much water, I think. It's so safe. Okay? Interestingly, however, I once did this research as part of an introduction. When you Google aspirin and I typed in the sentence, aspirin saved my life, and you got 56 million responses. And then I did the opposite. I Googled aspirin killed me, and you got 236 million responses. So people really like to complain on the web. And so what you see is a highly distorted picture of reality. Anyway, so there it is. That's how it's made industrially because the acetic anhydride is cheaper and not as corrosive as acetyl chloride. Conversely, by the way, for comparison, this phenol, which is an aminophenol, under the same conditions, of course, gets acetylated here to make the corresponding amide because this is more nucleophilic. And I'm just giving you this because that's the industrial synthesis of another very highly successful drug, Tylenol, which has its own quirks, but by and large, it's also well tolerated. Okay, electrophilic aromatic substitution, we've done that. Just repeating it. So phenol nitration, you get ortho-para, para dominates. You can do this for phenol ethers, no problem. Here's a Friedel-Crafts acylation, almost exclusively para here. The paper doesn't report any orthos, so if it's there, it must be there in minuscule amounts, and they just didn't even notice it. Halogenation goes very, very fast. If you do halogenation, just to give you an inkling for how much the OH function activates, at room temperature, you can't stop it. It just goes through all possible ortho-para positions, the two orthos and the para. Okay? If you want to stop at monobromination, which gives you ortho-para with para dominating, you have to go to low temperatures, minus 10 or minus 20, where the reaction can be controlled, and it stops at monohalogenation. Okay? Here's another case with methyl, where you block the para position, and you just get ortho. Okay? All of these are very good, high-yielding reactions. And finally, there is a very special electrophilic aromatic substitution that is really kind of stunning. It's called the Kolbe-Schmidt reaction. It was discovered by these two characters, Adolf Kolbe and Rudolf Schmidt. Schmidt actually lost his eye. As you can see, he's got this eye patch here. It looks like a pirate. At the age of 39 in an H2S explosion. And both of these discovered that when you take phenol in the presence of base, which makes the phenolate, okay, and then add carbon dioxide under pressure, you get electrophilic aromatic substitution, that would be one way to put it, of CO2. So this is the electrophilic carbon of CO2. It attacks the enolate anion. Another way of putting it is that it's an enolate attacking the carbonyl of the CO2, which is sort of reminiscent of an aldol. You can think it in both, either way. And that gives you this hydroxy benzoic acid, first as a salt, and then when you acidify, you get the corresponding carboxylic acid. And this is salicylic acid, actually, which is the precursor in the previous couple of slides that we used to make aspirin. And so this became a very important reaction because it makes the synthesis of aspirin on a large scale cheaply possible, and by a simple treatment of phenol with carbon dioxide under pressure. And what has puzzled people for a long time, and people I think now have a reasonable explanation for this, was the fact that you get only ortho attack. And the hypothesis is that in the phenolate anion, there is of course a counterion that is associated with the anion, and that positive charge appears to be attracting the oxygen of the carbon dioxide, and it comes in from out here, and then it swings around, and since when it's attached to sodium, this position is clearly much closer than the para position, the O- essentially directs the carbon dioxide to attack at this carbon here. And so again, if we look at it in terms of this electron pushing, it looks like an enolate anion, ignoring the rest of the stuff, attacking carbon dioxide, not unlike a Grignard attacking carbon dioxide to make a carboxylic acid. Right? Enolates are organometallics, right? Or you can think of this as a benzene ring that's very electron-rich because it spares an O- substituent, and this is an electrophile that does an electrophilic aromatic substitution here. And then in the end, you get the benzoic acid. And in the electrophilic aromatic substitution sense, as well as the enolate attacking sense, notice that the initial product, of course, is the typical intermediate of electrophilic aromatic substitution. Do the other resonance form here. So once you're done with the electron flow, since this is an enolate, this becomes a carbonyl. Okay, so you get this guy initially. All right, and this is nothing else but the keto form of the phenol. So this then undergoes tautomerization to the phenol by, under basic conditions, deprotonating here, reprotonating here. Aromatization, in other words, that follows the initial attack. That's as far as we want to go today. Thank you, and have a nice weekend.